As we've seen, when a light wave travels from one medium to another, some of the light is transmitted, some is absorbed, and some is reflected. So generally, if the index of refraction of medium 2, being the medium that the light ray is reflected from, is greater than the index of refraction of medium 1, which is the medium through which the light ray is travelling, then a phase change of 180 degrees occurs, or a pi shift. So as we can see in this case, because water is more optically dense than air, so the index of refraction of water is larger than that of air, then we see the reflected ray is pi shifted. So you can see this is the case by comparing the incident wave with the reflected wave. So this is analogous to our case of a string. So remember, if a wave travels from a thinner string through a thicker string, then part of the wave pulse gets transmitted and part of it gets reflected. And it gets reflected upside down in this case, because the wave speed in medium 2 is smaller than that in medium 1. So remember, the index of refraction was equal to the speed of light in a vacuum on the speed of light in a given medium. So given the index of refraction of water is larger than that of air, then the speed of light in water is smaller than that in air, which is analogous to this scenario of our string mediums. So that's one way you can remember if a pi shift will occur. Now in this case, our incident light ray is in water, and water has a greater index of refraction than air, being the medium which the light wave is reflected from. So in this case, no shift occurs. So you can see the reflected wave remains in phase with the incident wave. And generally, the phase of a wave does not change when it's refracted as it passes from one medium to another. So the phase shift only applies to a reflected wave, not a transmitted wave. So this is the general case where the incident wave is at some angle with the normal to the surface, and therefore given the index of refraction of the reflected medium is greater than the incident medium, then a pi shift occurs, and the reflected wave and the incident wave are out of phase by 180 degrees. Thin film interference occurs when light interacts with a medium whose thickness is comparable to the light's wavelength. So it's a very thin layer. And a typical example is a thin oil film or very thin layer floating on top of a puddle of water. So in this case, we have the incident light from medium 1, which is typically air, and that gets reflected at the oil interface, and some of it gets refracted, and this transmitted light gets reflected at the water interface and emerges from the oil film. So basically, these two rays are seen by the observer, and the interactions between the initial reflected light and the light exiting the thin film after being reflected from the second interface exhibit interference behavior. So this results in a superposition of two interacting waves that results in a single wave. So this is an easier way to look at it. So we have an incident wave in air, and part of it gets reflected, and part of it gets transmitted through the oil thin film, and this transmitted wave gets reflected at the water interface and transmitted through the oil and emerges from the thin film. And these two waves are superimposed into a single wave that's observed by the observer. Now the amount of constructive or destructive interference between two reflected waves depends on a relationship between the thickness of the film, the wavelength of light, any phase shifts or pi shifts of the reflected waves, and the angle at which the incident light strikes the film. So in our case here, we're going to do our quantitative analysis where the light waves travel parallel to the normal to the surface. So we avoid using Snell's law and do a simplified analysis. So recall for waves in the same phase, the path difference between them is an integer m multiplied by the wavelength of light, where m is an integer, so being 0, 1, 2 and so on. So this relationship is for constructive interference. So in this case, we refer to two waves being in the same phase, like in a double slit experiment. So the path length difference between the waves is a multiple of the wavelength. And for destructive interference, the path length difference is the integer m plus a half by the wavelength of light. So that gave us destructive interference. Now in our case here, the first reflected wave at the air-oil interface is ahead of this second reflected wave at the oil-water interface, a distance of 2 multiplied by the thickness of the thin film. So this is the path length difference between this first reflected wave and this second reflected wave. And now remember, a pi shift occurs if the index of refraction of the second medium is greater than that of the first medium. So oil has a larger index of refraction than air, so this wave over here is pi shifted. And for this second wave that was reflected at the oil-water interface, water has a smaller index of refraction than oil, then in that case no phase shift occurs. So given that one of these waves was pi shifted, then for constructive interference to occur, we need to add 1/2 a wavelength. So this makes sense that this would give constructive interference, because our first reflected wave was pi shifted and our second reflected wave was not. So these two waves are out of phase. So a relative phase shift occurred between the two waves. But if there was no pi shift, then this first relationship would give us constructive interference. So really have a think about that. So therefore for our thin film problem, destructive interference occurs where there's one pi shifted wave, where the path length difference is the integer m by the wavelength of light in this medium where the path length difference occurs. So to be specific, we take lambda 2, being the wavelength of light in the thin film. So again, if no pi shift occurs, or both waves are pi shifted, then we flip these two equations around for constructive and destructive interference. Now recall the refractive index was equal to the speed of light in a vacuum on the speed of light in the particular medium we're looking at, and the speed of light in the medium is equal to the wavelength by the frequency. Now when a wave gets transmitted and reflected, the frequency doesn't change, but part of the energy goes to the transmitted wave and part of the energy goes to the reflected wave. So the amplitude changes, the speed of light in the different mediums changes, and therefore so does the wavelength of light. So therefore for our incident medium, we have n1 is the speed of light on the speed of light in the medium, which is lambda 1 by the frequency of light. And similarly for our second medium, we have the speed of light on the wavelength in the second medium multiplied by the frequency. So in this case we have our incident medium and the thin film medium. So if we turn these around for the frequency, we get the frequency of light is equal to n1 lambda 1 on the speed of light. And in this second equation, we get the refractive index of the thin film by the wavelength of light in the thin film on the speed of light. And therefore the speed of light cancels from this equation. Now if our first medium is air, which is typical, then the index of refraction of air is very close to 1. So therefore the wavelength of light in the thin film is the wavelength of light in the incident medium, being air, over the refractive index of the thin film medium. So therefore if we substitute this into here, we get lambda 1 on n2. And if we make a bit of space here, so if we do the same for this second equation and multiply through by n2, we get the following relationship. And we'll just call this lambda in general, which refers to the wavelength of light in the incident medium. So these are our equations for constructive and destructive interference for our thin film interference problem. So remember that in this case, one of the reflected waves was pi shifted, so the waves were out of phase. But if there was no pi shift between the two waves, then the second equation would give constructive interference, and the first equation would give destructive interference. And we'll get some practice in applying these equations. Some practical examples of thin film interference include color variations that can be seen in soap bubbles, as well as oil films. So for example, you've probably seen a puddle with different variations in colors. And another example is anti-reflection coating, which is applied on the lenses of glasses to prevent glare. Now the spectrum of colors observed in oil films and soap bubbles arise from the differences in thickness of the film. So for a soap bubble, we'd have air, and then the variation in thickness of the soap bubble, and air again inside. So this variation in thickness enables constructive interference and destructive interference between the reflected waves from different incident wavelengths of light. So here we can see constructive interference between those reflected waves for different wavelengths of light. So for example, over here we have constructive interference for the violet wavelengths and blue wavelengths, green wavelengths, which we can see, and so on. And then in other parts of the soap bubble we have destructive interference, where we can't see the wavelengths of visible light. Now, anti-reflection coatings eliminate reflected light by applying the relationships between different indices of refraction, phase shift, or the pi shift of a reflected wave, and wave interference to create destructive interference from light that's reflected from the two surfaces of the coating. So for simplicity, we'll assume the incident light is normal to the surface. So the simplest anti-reflection coating has a thickness equal to 1/4 of the wavelength of light in the coating. So we'll just call that lambda c. And the index of refraction of the coating is larger than that of air and smaller than that of the surface upon which the coating is applied. So in this case, we're looking at glass. So in this case, what we'd get is a phase shift when the incident light wave is reflected from this surface of the coating, and the light wave that's transmitted, which is reflected from the surface of the glass, is also phase shifted. So remember, when light comes in from a medium that's less optically dense than the medium it's reflected from, then the reflected wave is pi shifted. So therefore both of these waves will emerge pi shifted, so they're effectively in phase. And therefore this relationship, which gives constructive interference if one of the waves is pi shifted, will give destructive interference in this case, where both of the waves were pi shifted and are in phase. So recalling the wavelength in the coating was equal to the ratio of the refractive index of the incident medium, being air in our case, on the refractive index of the medium from which the light was reflected, being the thin film or coating, multiplied by the wavelength of light in air. And remembering that air had a refractive index of 1, so if we divide this relationship by n2, we'd get 2t is equal to m plus 1/2 by the wavelength of light in the anti-reflective coating. So as we can see, if the thickness of the coating is lambda c on 4, then the path length difference between this reflected wave and this one is going to be 2 by lambda c on 4, or lambda c on 2. So this path length difference will cause these two waves to interfere destructively. So we can visualize this here. For example, if this is your eye and you had an incident light ray coming from here, and you had the anti-reflective coating on the interior surface of the glass, then using our scenario over here, we'd have air, the anti-reflective coating, and glass. Then the emerging reflected waves will interfere with each other, and therefore this reflection will be eliminated, which will eliminate glare. A wave of light with a wavelength of 490 nanometers is incident on an anti-reflection coating applied to a glass lens, and we're given the refractive indices of both mediums. Determine the thickness of the simplest coating that will result in destructive interference. While assuming the light wave is incident in air and is normal to the surface, and if we label these mediums 1, 2 and 3, then because the refractive index of air is less than that of the coating, which is less than that of the glass medium, then the wave that's reflected from this surface and the wave that's reflected from this interface are going to both be pi shifted. And therefore the formula for destructive interference for our thin film interference problem is 2 by the thickness of the coating by the refractive index of the coating is equal to the integer m plus 1/2 by the wavelength of light in the incident medium. So noting the wavelength of light in the coating is equal to the wavelength of light in the incident medium on the refractive index of the coating. So the thickness of the simplest reflective coating that will result in destructive interference is obtained by taking m equals 0. So using this relationship, we can write 2t is 1/2 by lambda 2. And therefore the thickness of the coating will be lambda 2 on 4. So if we substitute for lambda 2, we'd get t is lambda on 4n2. So now we can substitute for the given wavelength of light and the refractive index of the anti-reflection coating. So that's 490 nanometers on 4 by n2, where n2 is dimensionless. So therefore we'd get a coating thickness of 88.8 nanometers or approximately 90 nanometers.